So let's start the lecture. And this is like continuation of the previous lecture where we were talking about neural networks. And this segment, we are going to talk about non-linearity. So right now we have just looked into how we connect like set of neurons to different set of neurons and how like the data is propagated in a network, like from the input to the output. So first we will see like if we don't have non-linearity in your network, then how that reduces to like a single layer, irrespective of how many layers you have in your network. Okay, so let's talk about that first, and then we'll talk about like how we can introduce nonlinearity in your network. Now, we have seen like each layer you can define as a function, all right? And that function is, as we know, like the linear combination of all the values in your input. You use like the weights like to compute that linear combination, right? So that gives you like a value for one of the neuron, and you have several of those neurons, so you keep doing that. Okay, so you can represent that operation as a function. So let's say hx is that function, and that represents one of the layer. Now what will happen is this layer is again going to give you another set of neurons, right? So you have the input, you have this current layer, you will perform that linear combination for all the neurons. And then again, these set of neurons can act as input to the next layer, right? And if the next layer is again like a set of neurons, you can represent that as, let's say, function x, function f, right? So the output of hx is then is like treated as input to your function f, and you can keep doing that. So in this case, we have like two layers. H is the first one, f is the second one, and g is the output of a classifier. Okay, of course, so this is like just two functions, but you can compose many functions to make your networks deeper. Now the issue is, if you have this kind of compositionality, it doesn't matter how many functions you have or how many layers you add like on top of each other. At the end, it just reduces to a single function. All right, so let's go through that, how that's the case. So in this case, we have just one layer, right? So we have an input of three dimensions, x1, x2, x3, and your layer has 4 neurons, and these arrows are your weights. All right, so to get the value of like this neuron, you will compute like a weighted average, or you can say like a linear combination of all these inputs by the weights. So not all weights are shown here, because like from each from each input value, you should have an arrow to like all of the other neurons, right now, like for example, like x2, arrow from x2 to this neuron is not shown. Okay, so that's how you will get output of this first layer. All right, and then again you have a single neuron, which is like your output. Again, what it's doing is it's just taking linear combination of output of all these neurons. Okay? So kind of like you just have one function and one output layer. And a simple way to represent this neural network is this equation, and we have seen this equation before. Z over here is the output. W is like the weights. Okay, so let's say this is one represents like layer one. So this Z, if it's Z1, it's like output of this layer. It's not the final output. And B1 is the biases. Okay, it's a vector, and you will have one value for each of these neurons. X is your input vector, so it will be a vector of dimensionality 3. It will have 3 values. And this weight matrix is basically all the weights you have in this layer. Okay, it will be a matrix because you will have a column or a row for each neuron, right? So it will be kind of a 3x4 matrix here, and you can take like a linear combination of those weights with this input, and and you add those with the bias, like corresponding biases. That's going to give you these 4 values. All right, and those 4 values are represented by this Z. Okay, so now what you can do is you can add another layer on top of this, and let's say like the weights of those layers is this matrix W. So the superscript here 2 represents like a second layer. Okay, and these are the biases of the second layer. These are the weights, and you can see like the input to this layer is actually output of the first layer, the Z1. And again, this Z2 is output of the second layer, and you can keep doing that. All right. So now let's try to see what happens if we have lot of these layers and how that reduces to just a single layer. All right. So let's say we have this neural network which has 2 layers. So this is the first layer, this is the second layer. Now what you can do is you can try to solve this equation, the second equation over here. You just replace like this Z1 with the actual value, right? This value over here. So we replace this Z1 with this value, which is coming from the first equation. Now you can see that this is a weight matrix. This is a weight matrix. You can just do the multiplication and open braces. So again, this is going to give you a matrix multiplication. You will have X here. And then again, these are set of weights. You multiply that with this column vector B, which is set of biases. And again, you have this biases, which was already outside of this bracket. Now, if you multiply these two matrices, that's again going to be like some matrix, right? These are weights. And if you multiply this, this is again going to give you just a column vector. And if you add that column vector to this column vector, again, it's going to be like some vector, which again will be a column vector. Let's name that B. And whatever output you're getting from multiplication of these two matrices, let's call that W. Okay, so you can see that the formulation is exactly same as a single layer, right? So even if we add like 2 layers, but if you try to solve that, it reduces to a single layer. So which means that it doesn't matter how many layers you add, it's still going to be a single layer neural network. Okay, so let's see how we can resolve this issue. Okay, so that was the one issue, like if you don't have non-linearity in your network, it just doesn't matter like how many layers you have. It is equivalent to a single layer. The other issue is in your linear classifier, what you want is if you're making like small changes to your input data or your input sample, right? So you would want like very small amount of changes in your response, network's response, right? Because you're not changing a lot, so your results should also not change a lot. But in neural network, usually what happens is if you change like a very small if you change your input with a very small amount, what will happen is you might see like a very high response in your output. And that could be due to maybe the weights you have in your network, right? And like the kind of step function you're using maybe as activation, right? So that's not a good property, and we want to control that. Ideally, what we want is if you're changing like input with a very small amount, we should observe a very small amount of change in the network's prediction as well. Okay, so ideally, like if you're changing like with a very small amount, you should see a very small amount.